Hi, good afternoon, everyone. I am Dr. Andrew Raj Irdayaraj, currently working as a postdoctoral research fellow in Monash University, Malaysia, and I am here to present my work on the paper titled P2P Market-Based Distributed Frequency Control of Microgrid System. My paper ID is 68. Let's dwell into my work and my findings. The first slide of my presentation is on outline. The outline consists of the overall outline starts with introduction, then system model study, and then methodology and the findings of my research work, and finally into the conclusion and future scope. Uh, the main motivation for my work is on the focus of microgrids. As we all know today, due to the carbon emission into the atmosphere, the major emitter of the carbon emission is the power system. The conventional power system, the conventional fossil fuels such as thermal and other energy sources emits a lot of CO2 into the atmosphere. So to overcome these drawbacks and overcome these emissions, microgrids, which consist of multiple renewable energy sources, are integrated into the distribution grid, and which is evolving for the past decade. So as microgrids are deployed in the grid, it can be acted as an islanding microgrid, or it can be integrated with the main grid. So my research focus on the microgrid, which is acting in an islanded mode. So this microgrids, which is evolving right now, leads to deregulation of energy markets, which is nothing but open market like P2P energy trading happens between a prosumer and a consumer. And also this increase of microgrids reduce the environmental emission, and it also reduces the transmission loss and cost. It also eliminate the increase in load demand on the distribution side. So so the main objective in the microgrid is, the main two control objective is voltage and frequency. So my objective is to eliminate the frequency variation in microgrid irrespective of any load demand. So in terms of reducing the in terms of eliminating the frequency control, conventionally, there are three layers of frequency control in microgrid system. The first layer is the primary control layer, the second layer is the secondary control layer, and the final layer is the tertiary control layer. So the primary control layer will acts within milliseconds to seconds. This is the response time of the primary control layer. The secondary control layer will act from seconds to minutes. This tertiary control layer will act from minutes to an hours. So my main objective is on the secondary control layer, which is nothing but a secondary load frequency control layer, which is also called as a load frequency control. So the main objective is to maintain the frequency within plus or minus 0.2 hertz. So we also incorporated a P2P energy trading platform, which happens within the microgrid, which has 4 prosumers and 3 consumers. So the main objective of the P2P energy trading is to there will be a set of prosumers which are supposed to follow the demand made by the consumers. So the information flows from the prosumer, from the consumer, to a particular prosumer specifying its demand. So the main objective of the prosumer is to meet out the demand demanded by the consumer. So we need an additional control called as a supplementary control, which is generally not present in the traditional LFC scenario. So we need a structure, a specific supplementary control structure, whether the consumer demand is met by the prosumer. So when we incorporated these scenarios into the P2P scenarios into the microgrid, we cannot stick with the traditional control schemes like centralized or a decentralized control scheme, because it suffers from a lot of drawbacks, such as a single point of failure, and also the communication between each prosumers will not be there. So to overcome these drawbacks, we have developed a reliable control scheme, which is also known as a distributed control scheme, to solve the frequency stability of a microgrid system, which consists of n numbers of prosumers and consumers. So I have stated here in this slide, I have stated the drawbacks of the centralized control scheme, the decentralized control scheme, and why we are opting into a distributed control scheme. So the drawbacks I have stated here, where you can see it. In the distributed control scheme, the drawbacks are all eliminated. The drawbacks of centralized and decentralized control schemes are all eliminated. And we have incorporated the PID controller as a distributed PID controller, and the PID gains are fine-tuned or optimized using an adaptive hybrid atom search particle swarm optimization technique. So this is the system model study, where you have to implement our P2P energy trading in microgrid and our distributed control scheme. We consider a which is a simple microgrid system, which has a capacity of 750 kilowatt of capacity, where you can see four prosumers. The first prosumer, what we have considered here, is a diesel engine generator. The second one is a PV farm with an inverter, and the third one is a synchronous generator, and fourth one is a wind farm. So all these so each prosumers will have an individual controller, PID controller, and all these controllers are communicated in a distributed fashion. And there will be three consumers. One is a load, and another one is a battery energy storage system, which will store energy from the microgrid, and the third one is the EV aggregator, which will also act as a load. That means grid to vehicle. So this is the simple control. So these are all the control schemes, different control schemes, what I have discussed before. I have stated as a figure for better understanding. So where you can see how a centralized control scheme performs, and how a decentralized control scheme controllers are implemented in a decentralized fashion, which has an which there is no option of communicating, which there is no option for the controller to communicate between them. So these drawbacks are eliminated in the distributed frequency control, where all the controllers are communicated with in a sparse communication network, and how it has been implemented. So moving on to the methodology part, the first main primary objective for our research work is to develop a distributed PID controller. So the distributed control is a fundamental and complex challenge in a consensus problem. A consensus is nothing but it should come into an agreement. So distributed the controller which is in the microgrid can be communicated in any form in terms of consensus. So if you take there are many methods available in the literature, like a leader follower consensus is there, an average consensus protocol is there, a leader less follower consensus is there. Where we adapted a leader follower based consensus control has been implemented for our distributed controller. So the network structure, what I have shown in the system model studied, has been considered as a graph topology, where you can see the DG1, where you can see in the previous system model studied slide, the DG1 is nothing but the diesel engine generator, which will act as a leader, and the remaining three prosumers will act as a follower. So the reference frequency 50 Hertz will be given as an input to the DG1. The assumptions what we have made to construct this graph topology has been stated here. So this is the communication topologies of the DGs in MG in the microgrid. So to construct to construct a distributed PID controller, it can be done in the fashion of designing a proper pinning consensus algorithm. So the pinning consensus algorithm is stated here, which is nothing but the error frequency in the ith node minus the error frequency in the jth node plus the pinning gain. The pinning gain is nothing but the gain what I have shown before in the communication topology figure. And this is the ith frequency minus the reference frequency. The reference frequency is nothing but 50 Hertz. So here the N states the set of DGs that directly communicate with any DGs, that is DGI. So AS of xi is nothing but the weight of the information exchange between the agents. The agents is nothing but DGs in I and J. So if there is a communication between let us say for example DG1 and DG2, then A suffix ij will be 1. If there is no communication link between A suffix ij between 1 and 2, then it will be 0. So the pinning gain that is P suffix I is the pinning gain what I mentioned before. So for the DG1, P suffix I will be 1. For the remaining DGs, the pinning gain will be 0. So as I stated before, Fi and Fj are the frequency measured at node I and J, and F suffix R is the frequency, reference frequency, which is set at 50 Hertz. So next one is the design of distributed PID controller. The next step is to design an adjacency matrix A, which consists of the elements which I stated before. The adjacency values will be here. So the construction of the adjacency matrix is given here, where you can see how the adjacency matrix has been constructed here. So there will be 4 DGs, so we will get a 4 cross 4 matrix where the communication link between 1 to 1, this is A suffix 1 1, so A11 will be 0. So there will be a communication link between 1, 2, 3 and 4, so it all stands at 1. So similarly, there will be a communication link, two-way communication link between this is A suffix 1 1 1 2 1. This is 2 1, so there will be communication link between 2 1. The remaining there will be 2 2 and 2 3. There will be no communication, where there will be a communication between 2 4. Similarly, the constructions has been the matrix construction has been formulated. So next we have to simplify the equation here. Actually, this is a small mistake here. I have to be stated here. It's a DC engine generator, not a synchronous generator. So next we have to substitute these values into the equation what I have stated there. So we have constructed the distributed consensus controller from the previous equation. So so where we get this equation next. Next we have to construct for E2, E3 and E4, because we have 4 prosumers. So in the similar fashion these equations are constructed here, and we will obtain 4 equations. So E1, E2, E3, E4. So from these equations we can construct the diagonal matrix which is D, where you can see. So to check the stability of the constructed model, we can formulate the Laplacian matrix, which is nothing but L is equal to D minus A. So where we obtained an eigenvalue of 2, 4 and 0.2, where all is greater than or equal to 0. So the system will be stated as a stable system. So moving on to the next slide, from this we can construct, this is a simple PID controller and the error value, and the controller for the distributed PID system can be constructed from the equation 1, and we can frame the equations E1, E2, E3, E4 in MATLAB, and we have set up the model in Simulink, and we have controlled and we have deployed the distributed PID controller in the MATLAB Simulink platform. And finally, the objective function what we have considered here is an integral time absolute error to minimize the frequency between the change in frequency between the ith prosumer and the jth prosumer, or the DGI or the DGJ. So then moving on to the next slide, what I have presented here is where we all we might know is generally for a PID controller for a PID controller, what happens is the values of KP, KI, KD will generally be optimized using some conventional techniques like Cohen-Kuhn or Ziegler-Nichols type of tuning. But so to overcome the drawback, there are many optimization techniques, many AI-based techniques are available in the literature. So we have considered a hybrid atom search particle swarm optimization technique, and we try to convert that hybrid atom search which was developed by our team to convert that hybrid atom search optimization into an adaptive hybrid optimization. We have converted the parameters of both the atom search optimization and also the particle swarm optimization techniques with the help of an nonlinear mathematical equations, so that it will give an adaptive values so that the PID controller can deliver a better performance in terms of a wide operating range. So this is how we have these are the steps to be followed to obtain the gain values of the PID controller using atom search particle swarm optimization. And we have changed the velocity update equation of the particle swarm optimization. So where you can see we have added the chaotic version of an atom search optimization, and we have additionally added the cognitive behavior and social behavior of the particle swarm optimization into the velocity update equation of then atom search optimization. So these parameters, the omega C1, C2, or usually will be constant in the conventional atom search particle swarm optimization. We have modified these equation into a nonlinear equation, and we have convert this algorithm into an adaptive hybrid atom search particle swarm optimization. And then so moving on to the next slide, as I said earlier, in the microgrid system we have considered 4 prosumers and 3 consumers. So the consumer demands are to be met by the prosumers. So we have developed a contract participation matrix in the P2P energy system, and this P2P energy trading mechanism has been followed by the flowchart. So how the each prosumers will be communicated with the prosumers with the consumer demand. So we developed, and for the market clearing we have considered a double auction based pricing mechanism has been considered, and how the prosumers you might all know that how a double auction pricing mechanism will work, where the prosumers will be arranged in an ascending order, and the consumers will be consumer price will be arranged in the descending order. So once an optimal price has been attained, P2P market clearing price has been determined, and the market will be cleared. So this is how a double auction pricing mechanism will be performed. So we have generated a set of rules to clear the market for the to benefit both for the prosumers and the consumers. So the to be very too concise and precise, I will just say how we have developed this contract participation matrix as an additional supplementary control in the microgrid. So the contract participation matrix is nothing but the contract, how a contract occurs between, and how the energy trading occurs between a consumer and prosumer participating in the energy market. So where you can see the demands are in the are arranged in the rows, and the generation will be arranged as a columns. So the C11 is nothing but the demand 1 and the generation 1. So C11. So if you sum up the columns, you should get 1, so that we can come to a conclusion that all the demands made by the consumers are met by the prosumers. So no one will left out without meeting their demands. So the consumer will not the consumer who needs who needs power will definitely get the required power from the prosumer, from any prosumers, based on their market bid price. So this is how we have constructed the contract participation matrix. And moving on to the results and discussion, where you can see we have tested the same in the microgrid with a 0.2 per unit step load perturbation, and we have constructed a contract participation matrix, which is given in our paper, where the construction, how we have constructed the contract participation matrix in a very detailed manner, and I have derived the steps in the paper where you can see it very clear. So for that specific contract participation matrix, we have developed this response where you can see the distributed proportional integral derivative controller shows less undershoot, overshoot, and also settling time. And also we have shown some of the indices, some performance indices, like integral time absolute error, integral time square, settling time, rise time, peak magnitude, steady state error also. Where the distributed PID shows better performance than distributed PI and the distributed integral error. So the PID performance, what we have displayed is given here. And then moving on to the case 2, what we have done it here is we have checked the robustness of the proposed controller with the proposed control strategy, where we try to change the load for specific intervals, such as on the at 0 seconds, 15, 35, 50, and 75, where you can see the proposed PID controller performance in terms of the steady state performance indices, like settling time, peak time, rise time. It all shows minimum values, so it performs better. So when the microgrid is subjected to, since we have considered renewable energy sources like PV and wind, so we try to we didn't keep the source in a perfect constant way. So we try to change the sources. We try to change. We try to adapt to an intermittent nature of RE with the values collected from the real-time data of Malaysian Meteorological Center. So we try to feed it for around 500 seconds for both PV and wind, which is given here. So then we try to test the robustness of the proposed controller, where you can see here the settling time is much more better, and the undershoot is also much more better for the proposed distributed PID controller. So then additionally, we have also tested, as we are considering communication for a distributed mechanism. So then default we have to consider communication failure too. So we have tested the communication failure mechanism too. So we try to cut the communication link between DG1. Yes, at 30 seconds we try to cut the connections between DG3 and DG1, and also DG1 and DG4, where you can see a slight variation in the in the waveform, but that is also in a permissible limit of plus or minus 0.2 hertz. Then suddenly we have also injected another communication failure, which occurs at 50 seconds, which where the failure occurs between DG4 to DG1, and also DG4 to DG2 also disconnected. However, it all maintains at a stable state and is also within the permissible limit. So the proposed leader follower based the proposed leader follower based consensus distributed control strategy performs better in terms of all robustness analysis. So for the conclusion, to be concluded, we have implemented a distributed adaptive PID controller with hybrid atom search particle swarm optimization for the microgrid frequency regulation. We have used leader follower consensus control strategy, where the master controller, which is nothing but master DG, receives the frequency changes and sends references to the slave controllers, which is nothing but the remaining DGs 2 and 3 and 4. We have performed a lot of robustness analysis, and we have hence proved the proposed distributed PID controller with the help of hybrid atom search particle swarm optimization performs better when compared to the other integer order controllers like integral and proportional integral controllers. The future scope where we are heading towards is, instead of considering an optimization techniques, we are trying to adapt those hybridized techniques with the deep learning algorithms, and also zeroing a neural dynamics recurrent neural network controller, which is evolving right now in a deep neural network platforms. We are trying to doing it on a favor, and we are trying to modify that controller into an higher order controller, and also the practical applicability of the proposed FAL ZNT controller can be studied in real time. So we are also planning to do it on that area too. So that's all. So any questions, any queries are welcome. Thank you for giving me this opportunity.